we've used them for tensile and compressive stress and strain. So remember, compressive is when I was trying to squash something, and tensile is when I was trying to pull it apart. But it was axial. The forces were acting along the axis of your object. We also have to be able to deal with what's called shear stress, which is when you've got an object and you're trying to apply forces that are one up and one down across the axis, and it shears. And this is useful in be able to calculate. This is quite important in a number of places. For example, if I had a towing arrangement where I had the car pulling on this bit and the trailer hanging onto that bit, the strength of materials I'm interested in is a shear, because that's how it's going to give. It's not something going to pop apart like that or squash down and shrink. It's going to go like that. Okay. Also, this is how effectively a pair of scissors work. You've got a piece of paper and you push it on a blade there and a blade there, and it makes the paper do that. So this is a shear. So shear is something which is quite important, and we've got to be able to figure out how much shear stress or how much force it requires to cut something or to break something. So for example, we might have the situation I was talking about before. So we've got a pin holding a load together, so part of it's being pulled that way, so the car's pulling it that way, and the trailer is going back that way. And the question is, how much force can it hold before it breaks? So what force is required? So again, this is effectively the force is the car. We're going to use the same formula. It works perfectly well, the same formula. The area is the area which is going to be sheared. So the area that's going to move past itself effectively. So if I'm doing this, then the shear area is the cross-sectional area that's been moved. So again, it's just the cross-sectional area of that circle, and we can work out what force it can hold. And in this case, we're actually interested in the breaking force. So how much how much force can it hold before it goes past the ultimate shear? And we have a couple of language things here we need to use. So this formula technically is for compressive and tensile axial stress, and we rewrite the formula, same idea, but we use a torr rather than a sigma when we're talking about shear. So it's exactly the same idea. It's still stress, but now it's shear stress. So in this case, torr is the shear stress. And as we talked about before, I talked about the ultimate tensile strength on the last video, the video on factor of safety. We talked about ultimate tensile stress. We're now going to worry about the shear stress, the maximum shear stress that something can hold, and we talk about the ultimate shear stress. Ultimate shear stress. Okay, so we could have an example where, looking at this situation, a 20 millimeter pin, 20 millimeter diameter. I need to determine what it is. The 20 millimeters could be the length, a radius, so diameter. So a 20 millimeter diameter pin made of material with ultimate shear stress of, let's make up a number, 1701 kilonewtons, is used, kilonewtons are stress pascals, thank you, kilopascals, thank you, that was a bit silly, is used to hold a load. What is the maximum possible load? Okay, so I know that I've got a pin with a 20 millimeter diameter, and it's made of this particular material, and we're trying to figure out what load it can hold. So we're going to use this formula here, and what do we have? So we have, we know what the area is. Well, we know what the diameter is, so we can work out the area. So the area is pi d squared over 4 is pi times the diameter, 20 millimeters, 0.02 squared. I'm going to mare this morning. Divided by 4. Reach for the calculator. Put one with me. Probably don't actually need one for this bit, because 0.2 squared is going to be 4, which is going to cancel out on the bottom, but we'll be safe. Pi times 0.02 squared divided by 4 equals 0.03. I missed a 0 in my 0.003, makes more sense. 31 square metres. Okay, so that's the area. And then we know the ultimate shear stress, so USS 1701 kilopascals in this case. And I can work out what the force is that I can work with. So that's going to be torr in this formula, even though it's the ultimate shear stress. So I've got my formula. Torr is force divided by area. So force is the shear times the area. So 1701 times 10 to the power of 3 times 0.00031 equals, what have I got? There's a pen. 1701 times 10 to the power of 3 times 0.00031 equals 527.3. 527.3 newtons, because it's a force. So this particular bar made of this particular material, which is not a very strong material, can withstand 500 newtons. So if we get a force on here that's bigger than 500 newtons, it's going to cause it to shear, and actually the thing will break apart and won't carry the load it's supposed to carry. Okay, so that's the idea of shear stress. And the only other thing you need to know in that context is the concept of what's called double shear, or sometimes you even get triple shear. But it's a situation where, imagine you had the trailer, so that's the trailer drawbar, and the coupling that was holding it onto the car looked like this. Okay, so here's the car on this end, here's the trailer on this end. Trailer. I spelled it the same both ways. I wonder. Sometimes I've just got an O in there. Okay, and then you put the pin through here. So the pin goes down here, through that piece, down there, through that piece, down there, through that piece, and out the bottom. Okay, so that's the way that the pin holds the thing together. So it passes through the piece that's attached to the car twice, and through the piece that's attached to the trailer once. And in this case, the shear, where it's going to shear, it's got that piece and that piece. Okay, so this is what's called double shear. So even though you've only got the one pin, its surfaces are getting twice the action. So you've got two lots that you're trying to pull apart. So to actually make it break, you're going to have to get those two things to give up, or the weakest one will give up, but they're both carrying the load effectively. So the area that you'd work with in this formula is the total area. It's the two red bits joined together. So you have to work out the diameter, the area from the diameter, work out the area, and then double it before you put it into the formula. Or if you were working backwards, you wanted to figure out what diameter pin was required, you'd take your shear stress and your force and you'd work out the area, and then that would be the area for both bits. So you'd halve it to work with a single area to calculate the diameter. Okay? It's just the idea of double shear. So you need to count the total area which is going to be slid is the area that you're working with in these sort of questions.